Okay. Right. So this is a lecture on ionic conduction, a part of chapter 10 in chemistry 311. So we're going to discuss about transport phenomena of ions in an electrolyte system. So the basis of this is Ohm's law, where the potential is a function of the current times the resistance. Now this is in volt, I is in ampere, and R is in ohm. All right. Okay, you can also express it like this, where the current is equal to the potential over R, over the resistance. So if the resistance increases, then the current or the amount of charge passing, be that electrons or ions, will be small. So in a device like batteries or fuel cell, we want to minimize the loss by minimizing the resistance. So if your resistance is slow or low, then the current that you can use to do work will be high. All right. Okay. Now resistance is a function of a specific resistance, like a coefficient of particular system, times the length of that medium over an area. Okay. So the bigger the area, so you will have smaller resistance, right? But the longer the length, then you have a higher resistance. Okay. Just imagine like a cable. The longer the cable is, so the medium at which the charge particle, if in a cable it's electron, the charge particle electron has to travel, the longer the length means that the higher the resistance. But if the area or the interface, so if this is a sketch of a cable, so the area, let's say this is a tubular size or shaped cable, so the area, if the area is maximized, okay, then you can minimize the resistance. But then the length, the bigger the length, then the higher the resistance. Okay. Now the specific resistance with the unit of ohm meter is equal to 1 over kappa, and this kappa is the electrical conductivity with a unit of Siemens per meter. Here 1 Siemens is equal to 1 ohm, reciprocal of the 1 ohm. Okay, great. Now if we bring this idea of resistance and electrical conductivity into a concept of ions, so we will have the relations of the flux that equals to kappa times potential difference. Now the physics of this equation is that this is the flux of ion, right? Now we're focusing our discussion on ions in solutions in an electrolyte system. So the movement of flux of ion, okay, is equal to how much ions we have in the system and how big the potential difference. Okay, right. So the fluxless ion is actually current over area, right? This is the flux J, or this is also called current density. Because the unit is ampere per square meter. Right? So the flux of ion J is equal to the current over area. So current is how many charges moving over time. Okay. Now, if you remember physics 101 or 102 maybe, so the amount of charge is equal to current times time. Right? So we can then substitute this into I equals to Q, the charge over time. So this is charge over time times 1 per area. Now, if you're interested to know how many charge are flowing at a given time, so we have to look at the derivative of that, so dq over dt. Okay. Now, if we go back to the original equation, so we can substitute this with kappa times the potential difference. Okay. But what is the potential difference? So, in order for the electrolyte to move, in order for the ions in the electrolyte system to move, there must be a potential difference. Okay. Now, the potential difference will come from electronics in your device. So let's say you have an electrode, you have a system, okay, and you have an electrode with a certain area, and that's the positive pole, and this is the negative pole. Okay, you connect this to power supply. So the ions inside the container will move according, will respond. So the ions inside the container will respond to the electrical field. So the positive ion will move to the negative electrode, and the negative ions will move to the positive electrode. All right. Now, if we look at the potential difference, okay, so the negative electrode will have a more negative potential, so you have a low value, and if this is the distance x, so the potential difference will have this pattern. So the negative electrode will have a more negative electrode potential, electric potential, and the positive electrode will have a more positive potential. Now the slope here is the difference, d psi over dx, right? Because the difference here of the electric potential will be d psi over dx. Now then I can substitute here, which J of the flux becomes 1 over area times dq over dt equal to kappa times d psi over dx. Okay, because E is that the driving force of that makes the ion moves. So the ions moves because it responds to the potential difference between the two electrodes. Okay, and the potential difference is this line here, which is d psi over dx. Okay, so continuing in our discussion, the expression would be of a flux of ions in a solution, J equal to 1 over area times the amount of charge flowing over time. is equal to kappa. This is the number of that tells you how much ions you have in the solution, times negative d psi over dx. The negative d psi over dx, that's the gradient of electric potential you have in the system. In this case, the system is if we have a container that contains a solution with ions, and you perform an experiment to measure the conductivity. You will put a conductivity probe, and the conductivity probe will be connected to a box, the electronics that will measure the conductivity. Inside, at the tip of this conductivity probe, here will look like something like this. So it is composed of an electrode, two electrodes, of course, negative and positive, with a specific area and specific separation distance. Now, once a potential is applied, so there will be an electric potential difference between the negative electrode and the positive electrode, right? And if we sketch the electric potential over a distance x, so it would look like this. This is the value of the negative electrode. It will be more negative than the positive electrode, right? Now, the gradient will have a negative sign here in this term, because the positive ion will go to the negative electrode, and the negative ion will go to the positive electrode, right? They would compensate it. So the opposite ion will go to the opposite side of charge. This is why you have the negative sign. And here, kappa here is the electrical conductivity. Okay. And if kappa increases linearly with concentration, right, then kappa over C will give you a constant should give you a constant value. But this is not the case for most ions, for all ions, because of the interaction that we discussed in the class, ion-ion interaction and ion-solvent interaction. Okay. Now this expression kappa over C, it's called molar conductivity. So kappa over C is equal to molar conductivity. Okay. So when we plot concentration of the ions in the solution versus kappa over C, or this is the same as molar conductivity, instead of getting a straight line, we would get a decay, right? There will be a decrease as you increase the concentration, then the molar conductivity value decreases. Okay, and this is because of the ion-ion interaction and ion-solvent interaction. Now, this behavior is specific for strong electrolytes. Okay. So we will discuss separately strong and weak electrolytes, because the effect that is dominant in those two cases are somehow different.